All right. Good morning, folks. Hold on a second. Let me go ahead and let me start the timer here. And let's go ahead and let's get started with this. What I'd like to do this morning is I want to try to go ahead and finish up with the discussion of chapter 16. So again, we're only going to do 16.1. Unfortunately, we're going to skip qualitative analysis for a couple reasons. One, first of all, you probably will not see that on the AP exam. But secondly, because we can't meet this year, at least not right now. We can't do the experiments to kind of get you to see how qualitative analysis works. And it's best with qualitative analysis to be able to see how it works and be able to run the reactions and see how we use solubility product in order to determine then the solubility of certain solids in certain mixtures, and then we can be able to separate those out. So we won't be doing qualitative analysis, but we will cover, and I would like to try to finish up with the first part of chapter 16.1, where we are dealing with the solubility product constant, and then we'll give us a chance to finish talking about equilibrium. And hopefully today, if not today, then we will definitely start tomorrow. We want to get started into kinetics, okay? All right, let me go ahead then, and so please make sure you get that homework done, and remember the quiz. There will only be a quiz on chapter 16. You're not gonna, I won't be, you won't have an exam on chapter 16, so be prepared for the quiz. Obviously, it won't be a pop quiz here. Be prepared for it either on Friday, this Friday, or Monday, okay, next Monday. So please make sure you are prepared for that, okay? All right, so let me go ahead then, and let's pick up where we left off with on yesterday. Okay, we were talking about then how we can calculate. So we were able to calculate for the solubility. That is, we were able to calculate for the concentration of ions of a compound if we know its solubility product constant. And then what we were able to do also yesterday was we were able to calculate for the solubility product constant if we're given the solubility. Okay? And so let's go ahead then and let's work this one out. And I'm sorry, we worked this one already. And if you want to work it out again, please come by and hold on a second. I want to share the screen. All right, so there it is. So we worked out number 2 in your problem set yesterday. If you want to work this out again, please make sure you come by and I'll rework the aspect. But get some of the homework problems done, and that may help you also with this. But what I want to do is I want to share with you then what we calculated for yesterday. So we calculated the KSP for this, and this was for bismuth 3 sulfide. Okay? So bismuth 3 sulfide has the solubility that we were able to calculate for yesterday as 1.1 times 10 to the negative 73. So based on that solubility product constant, we expect then the equilibrium, when the equilibrium is reached, the equilibrium will lie far to the left. That is in the undissociated state. The solid bismuth 3 sulfide, based on this solubility, is practically insoluble. That practically none of it will dissolve at all in water. Okay, so that's what we expect then from this KSP. And so the question that we need to ask then is that can we use KSP to compare the solubilities of different substances? So let's take a look at a couple of other sulfides here. Let's take a look at the iron 2 sulfide. It has a KSP of 3.7 times 10 to the negative 19. Okay, and then finally silver sulfide. Okay, it has a KSP of 1.6, not 16, sorry. So 1.6 times 10 to the negative 49. Okay. All right. So looking at these KSP values, and if you were asked to put them in order of solubility, okay, of decreasing solubility, you would be tempted to say then well, iron 2 sulfide is the most soluble. It has the largest, that's the biggest KSP value, followed by silver sulfide, and then finally the least soluble then would be bismuth 3 sulfide. Okay, so we have then, if this was correct, and if this is what you were asked to do, you could argue, you would write then that this, it would be decreasing solubility as we go towards the decreasing solubility. as we go towards the red. Okay, most soluble, least soluble, and so that's what we would do based on the solubility values. Now, and that's what I kind of presented to you at the very beginning when we examined not the sulfides here, but we examined the chlorides. That's not quite actually correct. Okay, so let's go ahead then and let me ask you to consider what we have. Okay, so what we're gonna do is we're gonna consider this situation here. Okay, and I'm gonna go ahead then and let me go ahead and put this over here. Yep. All right, so let's go ahead and let's take a look at a question that's going to ask about them. We're gonna examine this. Okay? So is it correct to say then that the salt, an ionic compound with a higher KSP value, will always mean that it has a higher solubility? So let me answer this question together. Let's answer this question together by examining solubility product constant for two generic salts. Okay, so let's go ahead and do this for two generic salts here. Okay. And let's examine then a salt that is. Okay. Let's go ahead and write down AB. Okay, A, and then let's do AB2. Okay. All right, so we have two compounds the same. The only difference then is in the number of ions. Okay, so let's go ahead then and write down the KSP ion product constant. So AB, when it dissolves, then it's going to be then A plus B minus. Okay, with the AB2, when it dissolves, then okay, it's going to give us A2 plus 2B minuses. Okay. All right, so let's go ahead then and let's find the KSP. Let's write out the KSP values, the ion product constant for this here. This is going to be then the concentration of A plus times the concentration of B minus. Okay. All right, and here we have then the KSP value over here. If we write it the law of mass action, it's going to be concentration of A2 plus okay, times the times 2 times B minus raised to the second power. Okay. All right. So right now, hopefully you're already starting to see a subtle change here. But let's go ahead then and let's say that we were to solve for KSP. We can substitute it then x. Okay, I'm just going to go ahead. This will be x squared here. Whereas you see then that KSP for this one, if we substitute in x, it's going to be then. Hopefully you can write this. See this. It's going to be 4x to the third. Okay. So the KSP values are different. The KSP values for each one of these are different. The KSP for our, this is what we refer to then as a binary salt. Remember, we talked about this here back in first year chemistry. This is a binary salt. That means binary means it's only made up of two. Here we have two components here. This is what we refer to then as a ternary salt. Okay, meaning that there are 3 atoms that comprise this particular compound. Okay, and so if you take a look at then the KSP values, they're different. This is going to be a square, and this is a cube right here. So even though both of these compounds are made up of A's and B's, okay, we end up with different KSP values. Okay? So in order then, so the answer then is no. Okay, the answer is no. We cannot compare. KSP values do not necessarily provide us with an ability to compare solubilities of compounds. What we have to do, if we want to use KSPs in order to compare solubilities of compounds, we want to make sure then that the salts are of equal ions. That means then that they have an equal number of ions. That means you can compare the KSP values for 2 binary salts, or you can compare the KSP values for 2 ternary salts. But what you can't do then is you can't compare the KSP values for a binary salt and the KSP value for a ternary salt and say and make that determination about which one is going to be more soluble. Okay. All right, so the answer is no, and let's take a look at why. Okay, so the KSP values then they give us information about solubility, okay, but it doesn't necessarily tell us anything about a group of salts. Okay? So what we have to be able to do then, we have to also consider the number of ions that are present in each salt, and therefore, and so if a salt is a binary salt, it's going to yield 2 ions. If it's a ternary salt, it's going to yield 3 ions. Okay? And so what you can do is you can compare the KSP values for a similar set of salts, similar set of ionic compounds. So you can take a bunch of binary salts compare their KSP values. And absolutely, the KSP values in that case then will allow you to determine which ones are more soluble. You can take the KSP values for ternary salts, okay, a bunch of ternary salts, and compare their values. And you will then at that point also be able to determine then the solubilities of those compounds. What you're not allowed to do is you're not allowed to, what will not yield for you good information is you're not allowed then to compare solubility product constants for compounds that are not the same. Okay? So you have then a salt here, the bismuth sulfate that yields 5, okay, a pentenary salt here. You have a ternary salt right here, which yields 3 ions, and you have a binary salt here, which yields 2. Okay? So with those, you can't quite compare those and put them in order like that. Okay? So when the salts produce a different number of ions, that means they have the KSP values aren't necessarily useful in comparing the solubilities. Okay? All right, so that's it for what the solubility product constant is, how we can use the solubility product constant, how we can calculate for this solubility product constant, and how we can use the solubility product constant in order then to calculate for the solubility, the concentration of the ions in solution. Okay? All right. So with that said, then please make sure, I think if you get a chance to do set A, it's going to give you a chance to practice. But we do have to go on. We have to continue on. And I want to talk about the common ion effect in solubility as well. Remember, we talked about the common ion effect back in chapter 14 with acids and bases. Okay? And we saw then what happened when we have a common ion for an acid or base. It shifts the equilibrium one way or the other. We can use Le Chatelier's principle in order to understand that. We can use Le Chatelier's principle and the common ion to also understand how it will affect the solubility of a solute, of a salt. Okay, so let's go ahead then, let's take a look at silver chloride. So we have silver chloride in our example here. So let me go ahead and start out with that. Okay, so silver chloride as a solid, we know then that it has a fairly low solubility, but it will dissolve according to its solubility product constant into silver ions and chloride ions. Now, not a whole lot of it, okay, but there will be some of it. Okay? All right, so the question then is this, okay? If you add in sodium chloride, okay, and if you add in a certain amount of sodium chloride into our solution of silver chloride, what is that going to do? Well, sodium chloride, and you got to make sure you understand that sodium chloride will have a very high solubility product constant because it is practically soluble. It's almost completely soluble in water. Okay. All right. So into our silver chloride solution, we're going to add in sodium chloride. Now, if you notice, then the sodium ion is not going to do anything to this equilibrium. But if you add in the chloride ions, if the chloride ions go in there, what happens? It's going to increase the amount of chloride ions on the right-hand side of this first equilibrium here. So if we take a look at this first equilibrium here, it's going to increase the this number of chloride, the amount of chloride ions in solution. And so what is that going to do? It's going to send the equilibrium back towards the left. Okay? And what does that mean? We're going to get more of the solid silver chloride. So adding in this common ion right here, so adding in this common ion, adding in this sodium chloride, which has common ion chloride, okay, what it does is it's shifting the equilibrium towards the left, okay, it makes then the silver chloride solution here more insoluble. All that means then, folks, is that you are going to make more of the solid. The solid, you're going to shift the equilibrium back to the left, and therefore the equilibrium now is going to shift towards the solid side. Okay, and that's what the common ion does. Okay? And we can use Le Chatelier's principle to see then how it is that we have, if we add in a common ion, we can change the solubility of a particular solution. Okay, we can change that solubility by adding in a common ion. So let's take a look at some examples here. Take a look at some examples, and let's see what we have. So that's the common ion effect. Pretty straightforward, folks. We learned about the common ion effect back in chapter 15. We're going to apply it here to solubility. Okay. All right, so we're gonna. This problem here is asking us to find then what happens to the solubility of calcium fluoride. Okay, so let's go ahead and make sure we understand then that the equilibrium that they're asking us to consider right now is this equilibrium right here. It's going to be then. Let me go and do this. Solid calcium fluoride. Okay, dissociating small equilibrium product constant, we should expect then already the equilibrium is going to shift towards the left here, that the solid's going to be favored. Okay. All right. And we're looking then at this equilibrium right here. The KSP value for this equilibrium is 4.0 times 10 to the minus 11. Okay. All right. So let me go ahead and shift that equilibrium down here. Let's take a look at what happens here. Okay. So we have then. Oh, sorry. And so into this, yeah, so let's imagine that this is what's floating around in our container. Okay. Into this container right here, what are we going to add? We're going to add in sodium fluoride. Okay, so we're going to add in some sodium fluoride. So let me go ahead and write that in here. So we're into this, we're going to add in sodium fluoride. Okay. And so sodium fluoride, I'm sorry, let me go ahead and write it down here. Okay. Sodium fluoride going to have, and again, it is a 1A salt. Okay. So it's going to dissociate almost completely. Okay. So we're going to add in sodium fluoride, and we're going to add in a concentration of 0.25. We're going to have 0.025, molar sodium fluoride, which means then we're going to add in 0.025 molar sodium and 0.025 molar fluoride. Okay. If you notice then, sodium is not a common ion. It's not going to affect its equilibrium at all because sodium is not a common ion. However, adding the fluoride in here, adding the fluoride into that mixture right there, if you notice then, it should shift the equilibrium further back towards the left. Okay? Which means then we should have a less soluble solution. We should have a less soluble solution. And let's take a look at then. Let's find then what the equilibrium, what the concentrations would be at equilibrium with this extra added sodium fluoride. Okay. All right, let's go ahead then, and I'm going to do a couple things here. Let's go ahead and let's start out. And I would like to do, first of all, let's calculate for the concentration of the calcium fluoride without sorry, yeah, I'm sorry, no. Let's okay, without the common ion. Okay, so it's going to be Ca 2 plus 2F minus. Okay. All right, so we're going to use our ice table here. So we're going to have to use our ice table in order to get this done. Okay, so we don't have to worry about that. That's a solid. Okay, so in the beginning, that's going to be 0 molar and 0 molar here. Okay, we're going to add X, add 2X, and make sure you are okay with why this is going to be 2X. There's twice as much of the fluoride as the calcium. Okay, and so therefore at equilibrium then, let's go ahead then, it's going to be X and 2X here. Let's go ahead and set up the law of mass action for this one. It's going to be KSP. It's going to be equal to the concentration of calcium to the first power times the 2 times the fluoride to the second power, substituting in our values then. Let's go ahead and substitute our values here. We're going to have then 4.0 times 10 to the minus 11. This is going to be X times, and this is going to be 2X right here. So that's going to already be 2X. And that's going to be 2X squared. Okay. All right. So let's go ahead and solve for this one. This is going to be then 4.0 times 10 to the minus 11 is going to be equal to, let's see, that's going to be 4x to the third. Okay. And let's go ahead and let's solve for x then. Okay, 4x to the third. Let me go ahead and let's punch that in really quickly. So that'll be the cube root of 4.0. Let me do that all at one time. Okay. Let me go ahead and, sorry guys, I gotta, I always forget how to do this here. Okay, so, whoops, sorry. Let me grab my other calculator really quickly. This one's out of batteries. Sorry. But let me try this one real quick. You have then, oops, sorry. Oops, so. Okay. Sorry, 4.0 to the 11th divided by 4. Okay, I get here X being 5.5 times 10 to the minus 1, 2, 3, 4. Oh, I'm sorry, 8 point. Sorry. This is going to be 8.5, so it's going to be 8.5, 8.55 times 10 to the minus 1, 2, 3, 4, 5, 10 to the minus 5. Okay, so that's the solubility for calcium fluoride without the common ion. Okay, so let's go ahead then. We should expect then that the solubility should decrease as we add in the common ion. And let's go ahead and let's take a look at how that happens. Okay, let's go ahead and take a look at that. Okay, so okay, let's calculate for it. So we're still looking at this equilibrium again. So it's going to be calcium fluoride, solid. Okay, calcium ion, and 2 times the fluoride ion there. Okay, right. Setting up our ice table again. Okay. Okay, we're not worried about the solid. That doesn't have anything. We initially start out with 0 molar of the calcium ion. However, because we have this common ion here, we now have 0.025 molar of fluoride already in solution. Okay. All right, so with that said, then it's going to be plus X here, plus 2X again, and this is going to be X. Now this is going to be 0.025 plus 2X. We're going to put that in that way. Okay. All right. So with that said, then let's go ahead then and let's set up the law of mass action here. And so I'm going to go ahead and just substitute in, jump to the second step here. This is going to be then X times 0.025 okay, plus 2X. We're going to square that. Okay. All right. Now, what we can do here, which is what we could have done earlier, okay, is that since this KSP value is fairly small, the X here, this X here is going to be a fairly small X. Okay, that means then whatever X is, it's going to be small enough where it will not change this value here. Essentially, we're using the 5% rule. That's what we need to do. So we're going to assume the 5% rule here. Okay. The KSP is 10 to the minus 11, okay, and our concentration here is about 0.25. So let's go ahead then and let's make that assumption. So let's go and substitute in what we have here. This is going to be then 4.0 times 10 to the minus 11, okay, equal to X times 0.025, okay, squared. Okay, all right. So substituting that in, and let's go ahead and solve for X. Okay. I end up with 6.4 times 10 to the minus 8 molar. Okay. And that's exactly what we expect to happen. And that is, we expect then that the solubility should decrease. That means that we should expect the less of these ions floating around because of this common ion. We expect then that Le Chatelier's principle, when we add in the fluoride, it's shifted back to the left. And so therefore, the solubility will end up being smaller. It should end up being smaller here than what we had when without the common ion. Okay, so we have a greater concentration here of ions, okay, and we have a smaller concentration here of ions, which again is exactly what we expected when we add in the fluoride ions. Okay? All right, let's go ahead then and let's take a look at another example. Okay, so let me go and save this here. Let me clear that out. Okay, so please, well, no, actually, let me see here. Let's go ahead and do this. I'll try to find an example problem, another example from the homework for us to do, but we're going to move on here and make sure you take a look at that. I think these calculations end up being pretty simple. All right, because what I want to do then is I want to look at it. I want to go ahead and take a look at a topic that is similar to the common ion, and that is if we change the pH of a solution, if we change the pH of a particular salt, will that also have an effect on its solubility? We already saw then that with the common ion, there is an effect. We saw that already. It changes the solubility of a particular salt, a particular ionic compound based on that common ion. But will changing the pH of a solution also change its solubility? Okay, so the answer there is yes, and it depends. The answer is yes, but it depends. Okay? So with that said, then we're going to first examine then according to Le Chatelier's principle, and then we're going to go ahead and do the calculations. Let's take a look at two examples here: magnesium hydroxide and silver phosphate. Let's see how changing the pH, that means making it more acidic or making it more basic, will cause this solution to be either more soluble or less soluble. Okay? All right, so let's go ahead then and let's take a look at what happens with the first one. Okay, so let me go ahead and do this here. So we're going to look at two instances here. Okay, so let's talk about first what happens then when we increase the pH. So let's go ahead and let's talk about increasing the pH for the first solution. So we're going to increase the pH, okay, which means then we're going to make the solution more basic. Okay, so we're going to add into this example here. Then we're going to add more hydroxide. But in order to make it more basic, we're going to add in hydroxide ions. So we're going to add in hydroxide ions in order to increase the pH. Remember, increasing the pH meaning then we're going to make it more basic. Okay? So if we add in hydroxide ions, for example, we add in sodium hydroxide. So we add in the strong-base sodium hydroxide into this solution here. Okay? Will that affect the solubility? Well, absolutely, this will affect the solubility, because let me go ahead and share this. This is a perfect example of the common ion effect, because if you add in sodium hydroxide, you're going to increase the amount of sodium hydroxide here, which is going to shift the reaction back towards the left. It's going to shift the reaction back towards the left. Okay? And so by increasing the pH, which means then making the solution more basic, what we have done then is we have decreased the solubility because of the common ion effect. So we have decreased the solubility. We should expect then less of these ions in solution. Okay, the reaction is going to, the process is going to shift towards the left because you have the common ion here, and then you're going to have lower solubility. Okay, so that is if we make the solution more basic. Okay? All right, what if we do the opposite? Okay, what if we lower the pH? Okay, what if we lower the pH? Okay, which means then we're going to make the solution more acidic. Okay? If we make this solution of magnesium hydroxide more acidic, what would happen to its solubility? So for example, if we add into the solution hydrogen ions, if hydrogen ions, say, coming from hydrochloric acid. Okay, I'm sorry, this should be hydrochloric acid. Okay, so we're going to add hydrochloric acid into this solution, and we're going to make it, we're going to see what happens. Okay? Well, let's consider what happens here. If you add hydrochloric acid into the solution, do you see then this is not the common ion effect that's going to occur here, but it's going to be a reaction. Hydrogen ions, it's going to react with the sodium, the hydroxide here, removing that from the solution and thus sending the equilibrium towards the right. Okay? That means then you're going to get more solid dissolving. So by adding in more hydrogen ions, that is making the solution more acidic, what we have done then is we have increased the solubility of the solution. We're going to get more ions. We're going to get more ions in solution. So changing the pH here in either case here. So in case number one, where we are adding, adding in base, okay? Or case number two here, where we're adding in acid. Okay? By changing the pH, we have absolutely changed the solubility. We have made the solution then either more soluble or less soluble. Again, that's what you want to make sure you keep in mind. So the pH does affect. The pH will affect. The pH will affect the solubility of at least magnesium hydroxide. Okay, let's do the same thing for silver phosphate here. Okay, let's do the same thing. Let's do the same analysis. Okay, first of all, let's take a look at basic. Okay, a base. We're going to add the base in. We're going to lower. We're going to add in the base, and we're going to increase the pH. Okay, so let's see what happens when you add the base. Okay, and so we're going to try to increase the pH here. Okay, so we're going to increase the pH on a solution of silver phosphate, which means then we're going to make it more basic. Sorry, by adding in hydroxide ions as from, again, sodium hydroxide. Okay. All right. So in the first example here, adding in more sodium hydroxide, making it more basic, affected the equilibrium of magnesium hydroxide because of the common ion effect. Okay. If you add sodium hydroxide into this solution here. If you add sodium hydroxide in, and let's take a look at what happens when you add it in. Okay, let's see, add it in. Okay. It could react with that. Okay, now obviously it's not. There's no common ion here. There's no common ion here, and it won't do anything with the phosphate. So if the hydroxide gets in there, you can imagine then that it will react with, okay, the silver to form the silver hydroxide. Okay, so let's go ahead then and let's take a look at the KSP. Sorry, let me grab my table here. Okay, the KSP for hydroxides, and let's see, we have silver hydroxide. The KSP here is so we add this in, so we make this new substance. We have a new substance here, which is going to be silver hydroxide. Okay, and if it forms a solid, okay, that means if it precipitates out, okay, its KSP value is 2.0 times 10 to the minus 8. Okay. Silver phosphate has a KSP value, Ag3PO4, okay, has a KSP value of 1.8 times 10 to the minus 18. Okay. Now, again, we can't compare these two solubilities. We can't say then that the silver phosphate is less soluble than silver hydroxide. Okay, and so therefore you're going to have then this dissolving. The equilibrium is going to send it back. I'm sorry, it will dissolve and it'll send it back in that direction there. That's not going to be the case. This KSP value is already fairly small right here. So that means that we will form some of the silver hydroxide there. We're going to form it as a solid, and that's a process that we refer to as precipitation. Okay, so I should abbreviate. It's going to precipitate out. Okay, so it will precipitate. Okay, we'll get some of that. We will still have this as a solid floating around because look, the solubility here is very, very small, but we're going to form this compound as well, silver hydroxide. It's going to form as a precipitate, and if that happens, then just like what we did up here, it's you can consider it it is a chemical reaction. This is a precipitation reaction, if you folks remember from last year. So that means then we're going to remove the silver ions from the solution to make this new compound, which means then, in this case, it will increase solubility. It will increase the solubility because it's forming this precipitate right here. And that's what we see happening with the, by adding in a base, by adding in specifically adding in hydroxide. Okay, so we see then that in adding in this hydroxide here, making the solution more basic, we will increase the solubility. That means we're going to dissolve more of the silver phosphate. Okay. All right. So the opposite effect that we see then with adding sodium hydroxide into magnesium hydroxide. Okay. All right. So let's go ahead then and let's see what happens when we decrease the pH. That means then we add in an acid. Okay. So we decrease the pH, add in an acid. We're going to decrease pH. We're going to make this solution more acidic. Okay? And so we're going to add in hydrogen ions here in the form of, let's say, a hydrochloric acid again. Okay? And let's see what happens here. If we add in hydrogen ions, what you're going to notice then is the hydrogen is going to react with the phosphate there to form then the biphosphate anion. Okay? It's going to form the biphosphate anion, and we already saw with the biphosphate anion, in terms of its acidity, its Ka is very small. Okay, it has then a Ka, and I don't remember it off the top of my head, but it is a lot smaller than 1, which means then it also will not shift backwards. It's not going to reform. And so, with that said, then when we talk about this, okay, the equilibrium favors that, which means that when it forms, it will stay that way. So it's not going to go back to that, okay, because the K is fairly small. Essentially, what we're saying here then is this. If the hydrogen ion reacts with the phosphate to form the hydrogen phosphate ion, that hydrogen phosphate is insoluble. That's how you want to think about it. Because remember, in the same way that silver hydroxide here is insoluble, I'm sorry, and I'm running a little long time here. Just like this forms a precipitate here, and because that forms a precipitate, okay, the equilibrium is going to shift to the right. We can think of this as the same way, because this happens. This is going to be also, and I'm going to put this in quotes because it's not. We don't really think of it as solubility, but that is also going to be insoluble. This is also insoluble. It's a precipitate, which means that it is insoluble. In both cases, then, we form an insoluble product when we add that in. What does that mean then? That means then when we add in the acid, this also increases the solubility of silver phosphate. So with the compound silver phosphate, changing the either making it more acidic or making it more base, in both cases, we increase the solubility. With magnesium hydroxide, that's not the case. If we add in more base, we actually lower the solubility. If we add an acid, we actually increase the solubility. And so that's why I told you then that with the when it comes to solubilities here and the change in the pH, it depends. So the pH will alter the solubility of a particular ionic compound. Okay? I'm sorry, not will. We have, in order to determine then whether a change in the pH will change the solubility of a particular solid. Okay, we have to look at it. We have to do this analysis right here. Okay, so I'm going to go ahead and I'm going to save this for you, and we're going to practice this a little bit more tomorrow. I'm sorry, I was hoping that we could try to finish up with this today, but what we're going to do is we're going to practice this a little bit more, and we're going to talk about what happens then, and we're going to see we're going to apply what we did here, and this is all just kind of using the Chartier's principle, using what we know about chemical reactivity, and working this out. We're going to apply this tomorrow, and we're going to use this to understand how pHs will affect solubility, or if it will affect solubility. Okay. All right. We're almost done, folks. I feel pretty strong. I feel pretty good about us finishing up chapter 16 tomorrow, and then we will start chapter 12 tomorrow as well. Okay. All right. Have a good rest of your day, folks. And if you have any questions, please stop by. Stick around after. I'm sorry, after. Come by after my 7th period class tomorrow, and I'll take your questions. Okay. All right. Have a good rest of your day, folks, and I will see you tomorrow. Bye.